Hello and welcome to Parents, our YouTube channel for academics, competitive exams, and entrance exams. In the series of videos on physics, let us see what we have for you in the second of the three videos on electrostatics. Electrostatics, electric field. The topics which we will cover: first, electric field; second, electric field intensity or electric field strength; third, electric field intensity due to a point charge; fourth, superposition principle; fifth, electric lines of force, first due to point charge, second due to a dipole, third due to equal and like charges, fourth due to a uniform field, and sixth, properties of electric lines of force. Electric field. Electric field is a region of space around a charge or a system of charges within which other charged particles experience electrostatic forces. Theoretically, electric field extends up to infinity, but practically it is limited to a certain distance. Electric field strength or electric field intensity of electric field. Electric field strength at a point in an electric field is the electrostatic force per unit positive charge acting on a vanishingly small positive test charge placed at that point. Numerically, as we can see, plus q and plus q naught, so the force will apply in our upward direction, and in minus q and plus q, we can see the force of attraction F vector, where q is source charge and q naught is test charge, F is force and E is electric field. So electric field can be written as limit delta q tends to 0 F vector upon delta q, or E vector is equals to F upon q naught, or E vector is equals to 1 upon 4 pi epsilon naught q upon r square into r cap. The test charge is considered to be vanishingly small because its presence should not alter the configuration of the charges and thus the electric field which is intended to be measured. Since q naught is taken positive, the direction of electric field is along the direction of electrostatic force. Electrostatic force on a negatively charged particle will be opposite to the direction of electric field. Electric field is a vector quantity whose magnitude and direction are uniquely determined at every point in the field. SI unit of electric field is Newton per coulomb. Electric field due to a point charge. As we can see in this diagram, plus q is placed at the origin and a point charge is placed at P, x, y, z. So we can see that the force F vector is away from this charge q naught. R vector is the unit distance. Now force exerted on q naught by q is F vector is equals to 1 upon 4 pi epsilon naught q naught upon r square into r cap, or F vector is equals to 1 upon 4 pi epsilon naught q naught upon r cube into r vector. Electric field strength is given as E vector is equals to F vector upon q naught. Therefore, E vector as a function of r can be written as 1 upon 4 pi epsilon naught q upon r cube into r vector, or E vector as a function of r is equals to 1 upon 4 pi epsilon naught q upon r square into r cap, where r cap is the unit vector. As we can see in this graph between E and r square, this shows rectangular hyperbola, the nature of this curve. The electric field due to a point charge has a spherical symmetry. If q is greater than 0, then the field is radially outwards. If q is less than 0, then the field is radially inwards. Electric field in terms of coordinates is given by E vector as a function of r is equals to 1 upon 4 pi epsilon naught q upon x square plus y square plus z square whole raised to the power 3 by 2 into x I cap plus y j cap plus z k cap. Superposition principle. The electrostatic force experienced by a charge due to other charges is the vector sum of the electrostatic forces due to these other charges as if they are existing individually. As we can see in this diagram, there are so many charges plus q1 plus q2 minus q3 plus q4 minus q5. Now it exerts a force F12. Similarly, third particle will exert a force F13, fourth particle F14, fifth particle F15. So if we made a ray diagram of this, we can get this figure. So F1 can be written as F12 vector plus F13 vector plus F14 vector plus F15 vector, or we can write FA vector as a function of RA vector is equals to 1 upon 4 pi epsilon naught summation B is equals to 1 to n QA into QB into RA vector minus RB vector upon mod of RA vector minus RB vector का whole cube. In the present example, A is equals to 1, B is equals to 2 to 5. If the force is to be found on the second charge, then A is equals to 2 and B is equals to 1 and 3 to 5. The interactions must be on the charge which is to be studied due to other charges. The charge on which the influence due to other charges is to be found is assumed to be floating charge and other charges are rigidly fixed. Example, first charge floating is repelled away by Q2 and Q4 and attracted towards Q3 and Q5. The interactions between the other charges among themselves must be ignored, that is F23, F24, F25, F34, F35 and F45 are ignored. Superposition principle holds good for electric field also. Electric lines of force. An electric line of force is an imaginary straight or curved path along which a unit positive charge is supposed to move when free to do so in an electric field. Electric lines of force do not physically exist, but they represent real situations. As we can see in this diagram, these are electric lines of force. E vector. Electric lines of force due to a point charge. As we can see in this diagram, the charge Q is greater than 0, so we can assume it as a source, and we can see that electric field lines are going away from this charge Q is greater than 0. Similarly, for Q less than 0, we can see that it will act as a sink. All the charges will go in the charge Q. Representation of electric field in terms of field vectors. The size of the arrow represents the strength of electric field. Similarly, we can draw this diagram also. And for Q less than 0, as we can see, it will act as a sink. Representation of electric field lines in terms of field lines. This is the easiest way of drawing electric lines of force. Electric lines of force due to a pair of equal and unlike charges. As we can see, there are two charges plus Q and minus Q, and this is the electric lines of force representation. We can see that the electric lines of force emerge from plus Q charge and going into the minus Q charge. At point P, if we want to calculate electric field, we can draw a tangent and we can get the direction of electric field at this point P. Electric lines of force contract lengthwise to represent attraction between two unlike charges. Third one is electric lines of force due to a pair of equal and like charges. As we can see in this diagram, the two charges are plus Q and plus Q, and we know that like charges repel. So as we can see in this diagram, we will get a neutral point at this point N. Electric lines of force exert lateral sideways pressure to represent repulsion between two like charges. Electric lines of force due to a uniform field. As we can see in this diagram, there are two positive and negative charge plates, and electric field is going from positive to negative. Now, properties of electric lines of force or field lines. First one is the electric lines of force are imaginary lines. Second, a unit positive charge placed in the electric field tends to follow a path along the field line if it is free to do so. As we can see, this plus 1 coulomb charge flowing from positive to negative. Electric lines of force emanate from a positive charge and terminate on a negative charge. The tangent to an electric field line at any point gives the direction of electric field at that point. As we can see in this diagram, at point P we have to calculate electric field, so we draw a tangent. This will give the direction of electric field. Fifth, two electric lines of force can never cross each other. If they do, then at the point of intersection there will be two tangents. It means there are two values of electric field at that point, which is not possible. Further, electric field being a vector quantity, there can be only one resultant field at the given point represented by one tangent at the given point for the given line of force. As we can see in this diagram, If they intersect, then there will be two direction of electric field at that point, E1 and E2, and the resultant E vector, which is practically not possible. 6. Electric lines of force are closer where the electric field is stronger and the lines spread out where the electric field is weaker. As we can see in this diagram, the charge Q, capital Q and small q. Here Q is greater than Q. 7th, electric lines of force are perpendicular to the surface of a positively or negatively charged body. As this is a positively charged body, we can see that the electric field is perpendicular to this surface. Similarly, in this diagram, we can see electric field lines are perpendicular. Electric lines of force contract lengthwise to represent attraction between the two unlike charges. Electric lines of force exerts lateral sideways pressure to represent repulsion between two like charges. The number of lines per unit cross-sectional area perpendicular to the field lines is directly proportional to the magnitude of the intensity of electric field in that region. Delta N upon delta A is proportional to E. Electric lines of force do not pass through a conductor, hence the interior of the conductor is free from the influence of the electric field. As we can see in this diagram, there are two plates, positive and negative, and we place a solid or hollow conductor in between these two. So we can see that there is no field between this solid or hollow conductor. This is called as electrostatic shielding. Electric lines of force can pass through an insulator. This brings us to the end of the second video of the 3 videos on electrostatics. Please subscribe, like, share, and do press the bell icon for updates. Best of luck for your forthcoming exams. Thank you.